Hi guys, I'm going to review some of the most important concepts that are going to be on the Unseen Forces quiz to help you review and prepare for the quiz on Wednesday so that you can be successful. Okay, so it's going to be about unseen forces, which is electricity, magnetism, and also gravity. Now the quiz isn't really going to be about gravity because we're going to learn about gravity next, but you do need to know that gravity is another unseen force. We can't see the gravitational field, but we can feel the effect of it, right? Just like electricity and magnetism. Okay, so this first picture here is an electric field. This is how scientists model an electric field because it's invisible, we can't see it, but as we saw with the static stations, we can definitely feel a force, right? When we charged the pipe with the cloth, it pulled on the can, right, with an invisible force. A static electricity force, right? Same with the electroscope, which was a jar with the aluminum foil in it, and there was a wire coming out and curling at the top. When you charge the pipe and put it next to that curled wire, the aluminum foil pieces inside the jar separated from each other, right? Without even touching it. That was also because of static electricity, right? So we can't see an electric field, but we model it like this. So this shows a negative charge, and the field lines go towards the negative charge, and then a positive charge, the field lines go away from it, because that represents, if we plopped a positive charge in there, it would be attracted to the negative and repelled from the positive. So anyway, that is like how we visualize an electric field. This is a magnetic field, which if you use a compass next to a bar magnet, you can find the magnetic field. Or if you put the bar magnet, or any kind of magnet really, on some iron filings, the iron filings will spring into the shape of the magnetic field. So you can visualize it that way. Bar magnets, a lot of times they look like this, like they have the north and south poles labeled. Our bar magnets that we used in class don't have north and south poles labeled because they're a little bit different. They have the north and south poles on the faces of the magnet instead of the ends, but it's the same principle, it's the same concept, right? That if you put another magnet next to it, like if you put north next to north, it's going to repel, right? If you put south next to south, it's going to repel. But if you put south next to north, it'll attract. Same with north next to south, right? And then as far as charges go, positive and negative are going to attract because opposites attract. Positive and positive will repel, and negative will repel. Also, we've graphed the distance. As you get farther away from a charge, what happens to the force, the electric force. And you guys know this, that the farther away you are from a charge, the weaker the force is, okay? And the closer you are to a charge, the stronger the electric force. Same thing with magnets. The farther away you are from a magnet, the weaker the magnetic field. The closer you are to the magnet, the stronger the magnetic field. I like to think about this as like, if I have a magnet and I'm going to stick it on my whiteboard or on my fridge or something, and if I hold it far away from my fridge and then drop it, it's just going to fall to the floor. But if I put it close to the fridge and then drop it, then it can stick because it's close enough that the magnetic field can attract it to the metal of the fridge, right? Okay, so the farther away you are, the weaker the force, the closer you are, the stronger the force. That's important. Okay, and then this one right here, this is a model we've done on our warm-up before. So this shows a wire. These little blue circles with negative signs in them are electrons, because electrons are negatively charged. And electricity is the movement of electrons, okay? So this is showing electricity flowing through a wire. We've just zoomed in on the wire, and we see electricity flowing through. It's just electrons moving, right? Now, these red circles around the wire, they represent a magnetic field, okay? So anytime you have electricity running through a wire, a magnetic field appears around the wire. It induces a magnetic field. Electricity induces magnetism, okay? And we saw this in class when we did those electromagnets. We had a wire wrapped around a nail, and then we attached it to a battery, right? So the battery provides it with electricity. As electricity is running through that wire and going around the wire, around the nail, the magnetic field that appears around those wires, they add up, magnetize the nail, and make it so that we could pick up paper clips with our electromagnets, okay? So electricity induces magnetism, okay? It also works the opposite way. So that's what this simulation that we did, hopefully you guys remember, it was on the Chromebooks. It had a coil of wire attached to a light bulb, and you could drag this magnet, this is a magnet, right, with a north and south pole. You could drag it anywhere around the simulation, but when you put it through the coil of wire, you notice that the light bulb lit up, right? But if you stuck it in the coil of wire and then let go of it and let it just sit there and stop moving, the light bulb turned off again. So hopefully you noticed that in order to keep the light bulb continuously lit, you had to keep moving that magnet. You either had to like drag it back and forth through the coil, or you had to set it in the coil and then flip it, spin it back and forth, right? With that button that would let you flip it, okay? So a moving magnetic field is going to induce an electric current in this wire and light the light bulb, okay? So it's the opposite of this. Electricity induces magnetism, but also a moving magnetic field will induce electricity in a wire. That's pretty cool. So electricity and magnetism induce each other. Induce means to cause, okay? So they both cause each other. They work hand in hand. That's pretty important, and it's pretty cool too. We use this idea of magnetism inducing electricity. We use that to generate electricity that we use in our daily lives, right? If you have a spinning magnet next to a coil of wire, it'll induce electricity in the wire, and we can use things like windmills and water wheels and stuff to keep the magnet spinning using natural energy to induce electricity, to generate electricity, okay? So hopefully that is helpful, and hopefully that makes sense. Let's take a look at this really fast. So remember, north and south poles attract, north and north poles repel, and south poles repel. So if we had these two bar magnets here and we set them on top of each other like this, they would snap together, right? Because they would be attracted. These north and south poles are attracted to each other, and same with the other side. So these two bar magnets in this situation, they would snap together because they would be attracted to each other. Now if we flipped one of these magnets, then they would repel, right? And you guys in our magnet stations, you felt that magnetic force of the magnets repelling each other. It's actually pretty strong, and it's pretty impressive to feel that magnetic force. Okay, last thing really fast is charge diagrams, which we've done several times. So these are two of the static stations that we did in class. So let's look at this one first. So this is a person with their hair, right? So when you're starting out, the balloon and the hair have equal numbers of positive and negative charges, right? Then, when you rub the balloon on your hair, or if you rub the balloon on a cloth or something, balloons are really greedy with electrons. Now remember, protons, which are the red plus signs, cannot move. They're trapped in the nucleus of the atom. But electrons, or the blue negative signs, they can move because they're just around the outside of the nucleus. They can easily transfer from one atom to another. So, just the material that the balloon is made of is very greedy with electrons. So it's going to steal electrons from your hair. You can see that the hair that I've drawn here has a couple of electrons left, but the balloon has stolen a bunch of them, okay? Now, all the negative charges in this balloon are attracted to the leftover positive charges in that hair. The balloon has more negative charges than it does positive now because it stole a bunch of negative ones, okay? And the hair has more positive charges because it lost some of its negative charges. So the positive charges in the hair are attracted to the negative charges in the balloon. That's why your hair gets staticky when you rub the balloon on it, right? Some of you guys had your hair like, whew, it was pretty crazy. So that's what causes that, okay? Make sure you understand this and are able to draw something like this, okay? Now, I do want to talk to you about this one also. This is a pipe, the PVC pipe, and the soda can, okay? So if you remember, the pipe and the can, to begin with, have about equal numbers of positive and negative charges. So usually when I'm drawing it in class, if you guys remember, I just draw 3 positive and 3 negative charges in both of them, okay? And they're pretty equally spread out. Now, the pipe is the same as the balloon. It's really greedy with electrons. Remember, the positive charges cannot be transferred, but the negative charges, the electrons, can. So when we rub that pipe with the cloth is giving. It gives away its electrons, and the pipe is greedy and steals the electrons from that wool cloth. So now you can see this pipe has an overall negative charge. It has a lot of negative charges on it. Now, the negative charges in the can don't want to be next to the negative charges in the pipe. So they scoot over here to the edge, away from the pipe. I don't know if you can see those little negative signs there. And that exposes the positive charges in the can. Now, the positive charges in the can want to be next to the negative charges in the pipe, right? Because opposites attract. So that causes the can to be attracted to the pipe, which is pretty impressive to watch, I think. And I like to like move the pipe from one side of the can to the other and make it like change directions. It's pretty impressive to see that unseen force. And what causes that attraction is these electric fields that we can't see, but we model them like this. And that's what's causing this, okay? So hopefully that was helpful. I'm going to leave this up in case you need to look at it. I'll just hold it up while I'm talking. Hopefully that was helpful. If you have more questions, please ask me, because I would love to help you and I want you to be successful. So good luck on the quiz.